Hello, students. Today's topics of the study is the p-pi d-pi and p-pi back bonding in the BF3 molecules. In the p-pi back bonding, the orbitals involves all the p-pi and p-pi orbitals of the both the atoms. If you consider the molecules of BF3, then the boron and fluorine atoms having the p orbitals, that p orbitals involved for the sigma bond as well as the pi bonds. This pi bond formation is called as p-pi back bondings in BF3 molecules. This p-pi back bonding is due to the f orbitals having the sufficient amount of lone pair of electrons, which give the lone pair of electron to the boron atoms for completion of its octet. As the boron is the electron deficient atoms, it provides the lone pair of electrons to the borons. The 2p orbitals of the fluorine atoms having the lone pair overlap the sideways with the empty 2p orbitals of the boron atoms, give rise to additional fluorine borons bond form, which is the result of the p-pi back bondings. Here the structures are given. In the structures, boron atoms having the 3 valence electrons. These 3 valence electrons involved in the pi bondings and the formation of the covalent bonds. So total number of electrons available for the boron atoms after the formation of covalent bond is 6 electrons, 6. But as the fluorine atoms donate the pi electrons to the boron atoms, it becomes the p-pi back bondings. This extra electrons is completely donated by the fluorine atoms. It is a covalent bond. It is a coordinate bonds, but by using these atoms, boron also completed its octets. So the lone pair overlap sideways with the empty 2p orbitals of the boron atoms, give rise to the additional fluorines dash borons, and boron fluorine bond forms, which is the result of the p-pi back bondings. As a result of this donations, electron deficiency of the boron atoms gets compensated and its Lewis acid character decreases. The tendency for the back donation is maximum in case of fluorine due to its small size. Tendency of the back donation is maximum in case of the fluorine due to its small size. So in this case, in the 2p orbitals of the fluorine atoms having the lone pair overlap sideways with the empty 2p orbitals of the boron atoms, give rise to the additional fluorine and the borons bond form, which is the result of the p-pi back bondings. So as a result of these donations, the electron deficiency of boron atoms get compensated and its Lewis acid character decreases. The tendency for the back donation is maximum in case of the fluorine due to its small size and more interaction between the 2p 2p orbitals. Hence, it is the least acidic. The strength of the Lewis acid is the Bf3 less than BCl3 less than BBr3 less than Bi3. This is the strength of the Lewis acid characters. Next is the application of Bf3. In the application of Bf3 molecules, Bf3 is used as a Lewis acid in a chemical reaction. It can be used as a catalyst in the Friedel-Crafts reaction also. It is electron deficient, hence used as a electron pair acceptors, and these electron pair acceptors form the coordination covalent bonds. So this is all about the applications of the BF3 molecules. Now, next point, draw the structure of the BF3 and why does it called as Lewis acid, and write its any three applications. Write its any three applications. BF3 molecule, BF3 molecules are given here. In that clearly mentions the bonds. The boron atoms having the 3 valence electrons, 2 electrons of the s orbitals, 2 electron of the s orbitals and 1 electrons of the p orbitals that involve in the bondings. The chemistry of silicon and germanium. Next point is the chemistry of the silicon and germanium. Silicon and germaniums are also the p block elements. Silicon, germanium are the family of the carbon family elements. Group 14 elements, it is comes into the class of the group 14 elements. Consist of the group 14 element consist of the carbon, silicon, germanium, tin, lead. Out of its, germanium is the rare element. Out of its, germanium is the rare elements. Carbon and silicon are the most abundant element. Carbon and silicon are the most abundant element by weight in the earth crust. Germanium is only found as the traces is some silver and the zinc ores. Electronic configurations: atoms carbon C6. Electronic configuration is 1s2, 2s2, 2p2. Silicon's electronic configuration is the 1s2, 2s2, 2p6, 3s2, 3pz. Germanium 1s1, 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6. Tin 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p2. Lead 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p6, 6s2, 4f14, 5d10, 6p2. From the electronic configurations, it is clear that these elements have the 4 electron in their outermost shell, that is they have the 4 electrons, that is ns2 np2 trained in the property. Atomic radius and the ionization energy. Atomic radius of the element of the group 14 increases to some extent with the increase in the atomic numbers. The ionization energy decreases as we go down the groups through which is not seen regularly. This irregular trend because of the intervarying of the orbitals shieldings. Next is point is the metallic and non-metallic characters of the silicon and germanium families. Non-metallic character increases as the atomic number decreases. First two elements, carbon and silicon, are the distinctly non-metals. Germanium is a semi-metals with some metallic properties, while last two elements tin and Pb are the distinctly metals. The increasing tendency to form the metals M2 plus ions and acidic basic nature of their oxides hydroxide also confirm the increase in the metallic character from the carbon 2 lead. Oxidation state and the inert pair effect. Outermost valence electrons are ns2 and p2 naturally either loses 4 electron and gain the 4 electron, acquire stable configurations. Total ionization energy is very high from the removal of 4 electrons. Very high amount of energy required, hence the plus 4 oxidation state number present. These elements do not form the minus 4 oxidation state. The only alternative left is the share the 4 electron with the outermost elements. When they form the compound in the plus 4 oxidation state, the one of the ns2 electron is excited to the higher np orbitals and form the 4p half filled orbitals. The stability of the plus 4 oxidation state decreases and that of the plus 2 oxidation state increases from carbon to lead. This reluctance of the ns electron pair taking part in the bonding is called as inert pair effect. Silicon forms a stable compound like SiH4, SiCl4 etc. with plus 4 oxidation state. Germanium and tin form the compound in a plus 2 and plus 4 oxidation state. Pb plus 2 oxidation state is the oxidizing agent and the more stable than the plus 4 oxidation state. Due to the inert pair effect, Pb2 plus is more stable than the Pb4 plus. Stability of the lower oxidation state increases, that of the higher oxidation state decreases. In the group with increasing the atomic number from carbon to lead. So the friends, remaining part we will cover in the next lecture, that is melting and boiling points. Thank you.